5 minutes to go.
Okay, great. Well, good morning, everyone. Glad to be here. My name is Cesar Briceño. I'm the telescope scientist at the SOAR 4-meter telescope on Cerro Pachón. And I'll be talking today about SOAR, the Alert Event Observatory Network on the SOAR telescope. So it's been a while since several reports, like the Emma Green report, that was organized by NSF, and other meetings like the one in Arizona, maximizing science in the era of LSST, came up with the conclusion that there really is an important need for not only for resources for follow-up of LSST target, but somehow coordinating and optimizing those resources so as to make an efficient follow-up ecosystem, if you want to use the word. And in particular, the benefits of facilities like SOAR, Blanco, and GEMINI was recognized from early on. So, as I mentioned, the idea is build time domain and transient follow-up ecosystem consisting of different facilities ranging from smaller up to 8-10 meter class telescopes that can work in an efficient, coordinated manner. And in this diagram that puts the different actors of the system, the surveys, the brokers, the TOM, what I'm focusing now is on the facility side, this part in the red box. So the stage for development of AEON was largely brought about by a grant that was won by Las Cumbres Observatory and MSIP grant, and gave some money for an initiative that they were carrying out to develop and incorporate, develop a follow-up ecosystem, incorporating larger facilities to their existing network, using the experience and the know-how that they already had. And so conversations started happening between NOAO and Las Cumbres, specifically again SOAR and GEMINI, about how to bring this about. And eventually, we thought that SOAR would be a good candidate to be selected as a pilot facility for bringing the bigger guns into the follow-up network. And GEMINI basically just following right behind that. And so even from early on, like as Brian will mention, GEMINI started working also in the same path. Advantages are clear. I mean, these are facilities that are co-located with LSST, so there are ideal follow-up engines that you can, and resources that you can use. So basically, AEON is a system that consists of several, up to now, SOAR, Las Cumbres, NOAO in general. Now it's not NOAO anymore. I should have updated this, but NOAO is now deprecated. But GEMINI. And the idea is that more and more facilities, I mean, this will just grow up ideally over time. And these facilities communicate through observation interfaces to either user interfaces or TOMs, and probably, for heavy users, power users will be, of course, TOMs, and through that they get their influx of, alerts from brokers and so on from various surveys, and And then, of course, as targets are observed, that knowledge gets fed back into TOMs and brokers, and it sort of closes the loop. So that's the general idea of AEON. Now, SOAR in particular had special requirements, as will any facility have. And here's where I want to explain a little bit more, because it may be useful for other facilities that may want to integrate into the system later on. Each telescope, each institution has different needs and different limitations, also requirements. In particular, SOAR will not be robotic, not now, not in the near future, or probably the midterm. We plan to always have a carbon-based sentient being at the telescope, or really smart and capable telescope operators. But that's just the path we decided. On the other hand, we can't afford more staff to operate a queue which is highly configurable and intervenable, and so requires people being there to sort of fiddle around with it, and that sort. We can't do that. We don't want to do that. What we can do is have a highly automated queue that comes into SOAR, and we don't care about how things are, how the queue was assembled or built up. That's not our problem. That's external to us. What we want is an automated queue that comes in, and it can be run by our telescope operators with minimal supervision from scientists. Therefore, with basically the same staff doing almost essentially the same job and tasks that they need to do, that are doing right now, we can do this. And so the way to bring this about is do a fully automated queue, generated in this case by Las Cumbres with their own software. This queue is non-editable. Therefore, it's no decision making happening at the telescope. You just run it, okay? And the telescope and instrument, of course, need to be highly automated in order for this to be to happen, even though it's not robotic. So the software architecture we came with basically consists of what we call the SOAR queue manager. It's built basically on Python 3 and MongoDB. It manages the communications with Las Cumbres via APIs. And so, as we will see, a lot of the work was defining those common API. So everything here is SOAR. Out there is Las Cumbres, okay? So a schedule is ingested, coming through us. It's managed by the SOAR queue manager. Also, it has to publish our status to the network. Hey, SOAR is alive. No, SOAR is down because of weather, because of technical reason, whatever. And it has to update the status of every observation, and of course, push the observation, the raw data up to the system, right, to the basis. Internally, it has to parse all the information blocks coming in those JSON files that are related to every single observation and convert them into language that the instrument and telescope can comprehend and make things happen here. Point the telescope, move a grating, put filters, so on. And then we have a web interface, which is how the queue manager communicates with the human being there who is running things, and that person can therefore supervise and check things that are, and stop processes and so on. So just a small digression that to show AEON is of course a collaboration of a lot of people. Rachel is the project scientist for Las Cumbres. Steve for now for NSF OIR Astrolab. me for SOAR, Brian for GEMINI, and we have our team of super duper programmers without whom this, of course, will never haven't got anywhere. And our charges were basically these: implement the changes to the Las Cumbres software scheduler in order to make it work and talk and communicate with SOAR. That's it. Define the APIs and implement them. Then incorporate SOAR into the network using the Goodman spectrograph and actually execute observations on dedicated AEON nights, coordinate data pipelining, archiving, and then bring GEMINI on other facilities. The scope of the project was basically through 2018 and 19. It's basically just 3 phases. An interface demonstration, just make sure that the APIs were fully described, well understood. We could actually make software talk to each other between Pasadena and Chile. Then by early this year, we conducted a single night of observations. A lot of it was manually running some things, but actually testing the pipes and the hardware in all the structure in the system. And then we started sort of full operation in a share risk mode in the 2019 B semester, where we actually are running now a set of selected beta testers from among the approved programs for the 2019 B semester, and those programs are real science programs that are being run in the specific AEON nights. There are some things that are still in the works. For example, our star acquisition on the slate is manual. That we eventually want to automate that, but that was not in the scope of the original project, so that's not being done right now. And also guide star acquisition, and then real-time processing of the spectra. We already have a working offline pipeline for SOAR that produces 1D wavelength calibrated spectra like that, just basically 2 commands, and it spits out your resulting data. What we're working right now is implemented that as a real-time thing. So as every spectra comes out of the instrument, it will be saved not only the raw data, but the reduced 1D spectrum too. So we started with an initial configuration. And I have to mention, for people that know, or well, for those that don't know about SOAR, the Goodman spectrograph is like a Swiss knife kind of thing. It's super highly configurable. So there's no way we could provide support for any possible configuration people can think of. So we just basically decided, okay, we'll just support the basic, most popular configurations on Goodman, especially for starters. And then we'll maybe add on several more ones as demand, depending on demand. And so basically we're working with 2 low resolution modes that span the whole optical wavelength range, close to basically covering H alpha, at rest, I should say. And an imaging mode, okay? Everything is working in 2x2 binning, and a single readout mode. I mean, SOAR Goodman, you can select any readout mode, any binning. I mean, that's how, so we're just, and with this slits, we have a multiplicity of slits that we can use, but we're just using this. And we'll always have the atmospheric dispersion corrector in. That allows people to select any position angle on the sky they want. It defaults to 0 if you don't specify anything. But some people may want specific, and so they don't have to worry, I can't because it has to be the parallactic angle, anything like that. And as I mentioned, acquisition, guide star acquisition, so on is manual. So what's the workflow like? Okay, so you have some scientists somewhere using either the Las Cumbres observing portal, or they can be using their own TOM or whatever. Through that, they make observation requests. That goes to the Las Cumbres scheduler. Here, all the magic happens. It sort of sorts things out between different programs and so on, and builds up schedule. And that schedule runs automatically. It updates automatically every 15 minutes or more frequently if there are changes, if there are new observations pushed into the schedule, especially if there is a rapid response, things like that, then the updates will happen more rapidly. Our system, the SOAR queue manager, is polling all the time. Do you have anything for me? Do you have anything? Oh, there's something. Okay, so it downloads it. Okay, interprets it, sends it to Goodman, and and through the TCS to the telescope dome, moves everything, does the grading, filter changes, everything, and so on. And other than the target acquisition, does the observation. Then the observation, the data gets written to disk. The SOAR queue manager now adds a few extra things to the FITS headers, things like the prop ID, like the proprietary period keyword, things like that, and then pushes everything back, both the data and telemetry about how the data was taken, back to this Las Cumbres. So just to show you how the observing portal works looks like for SOAR, is basically the same. The only thing is you'll get your program here, and depending if you had time on SOAR, then the Goodman instrument will show up and so on. Of course, this is not a good sample because it actually shows the Sinistro imager, but well, whatever. So so then what happens on the SOAR side? So what the user sees is either their TOM in action or the observing portal. That's all they care about. Let's say I'm using the observing portal. I put in my observations, and I go to the. I haven't shown the other pages, but where you get shown which observations you have been observed, which are scheduled, which have been canceled for whatever reason, and from there you can get your data. Fine. Now, on our side, what's going on? Okay, so this is what's going on. Every afternoon, we do the calibrations. In the afternoon, and then at sunset, of course, our telescope operator opens the dome, and it's the telescope pointing, active optic system, and so on. When it's ready, and starts the SOAR queue manager, makes the connection to LCO, immediately you get a schedule downloaded, and once the first observation is queued to start, and it's actually the start time for that observation, you'll have to authorize the slew to the first object. And that's because we have implemented a safety limit. That's not hardware related. It's just policy that we decided we don't want the telescope to move to do any move larger than 15 degrees on the sky on its own without the operator authorizing it. And of course, the first move will need authorization, right? Because you're starting from zero. So they just click a button and it goes. They do the first target, and then you start doing everything else. And then again, unless the move is large on the sky, the telescope will just go automatically to every new target and so on and get things started. And as we will see in a minute, I'll just only stop when the acquiring phase needs to go on. During this time, the operator can always disconnect from the network. There's a button for that. And that could be because we got clouded out or wind or whatever kind of weather conditions. There's only two reasons, weather or technical. That basically covers everything, right? And then at the end of the night, it's done. So how does the web interface look like? Of course, it has a login page. And then once you get into that, you'll see that it has four basically general areas. Like the control area up here where the buttons are to start, stop the queue, connect, disconnect to LCO, connect, disconnect to our instrument Goodman. The idea that is because we may decide in the future that we can add other instruments. And so we already had that capability there. There is an execution area. This is where your current observation is happening. Yes. There's a staging area and then an exit area. Staging area, this is an input queue. This is a queue we just read from Las Cumbres. It's queued up here. And this here is where things are going this way, and then they get done, and then they come out this way. And this is where your observations, successful or not, come out. This one was unsuccessful, for example. That's why it's flagged in red. The afternoon calibrations are again done programmatically. You just, here in this case, we selected 2 sets of bias frames, and then you just start calibration and it just runs. And the same thing does for flats, biases, and focus here is because you have to focus the instrument for every different configuration. And you do that, you focus the instrument, again, it runs through the thing. It calls, it has a Python library that our people built. That one calculates the focus and then returns the appropriate value, says this is a correct focus, and then once you got that, then you can go on and do the flats and biases and everything. Then when you come to the observation part, again, if you go to the staging area, or for that matter here, if you click on any of your target, you get an expanded view immediately. And so it tells you all the information about that target, the start time, the end time, the target name, RA, DEC, blah, blah, blah. And it tells you the configuration it's doing. In this case, you probably can't see, but it's a spectrum with a 400-line grading. If I clicked here on the blue thing, it will just expand again this little box and tell me the details of the configuration. And I click again, then it just folds back, right? So the guide star acquisition. So when you are on target, and in the execution area, what happens, we have different little buttons, LEDs here, that light up green when each mechanism is done. You know, this is for, okay, I have to put in the comparison mirror, I have to turn on the comparison lamps or turn them off, I have to move to the target, I have to set up the camera and grading angle for the spectrograph. Gears is just everything that is filter related, that sort of stuff. So as you can see, as every part of the system is coming into place, and when you come to a line, it'll just pop up this and say, please put your star, do your thing, right? And so the operator will just quickly find the guide star and then put the star on the target on the slit if it's spectroscopy. If not, it'll just click done. And then the nice feature that we have is we have a dynamic finding chart. So if you click here on the target name, you'll have a pop-up through an Aladdin plugin with your target. And you can zoom in and out and things like that, and we can change the type of the survey image that we're showing, so on. And then once that happens, you start your exposures, tells you the readout time. It keeps count of how many exposures you're doing, and you see things happening here. If you want to disconnect, then you have a menu up here which says whether technical. You select either reason, and then you click disconnect, and you're disconnected. So we had, as I said, we started this semester in sort of testing mode with 8 science programs. A total of 20 nights were scheduled. This comes, the 20 nights are about 200 hours, which is what was approved by the Time Allocation Committee to these collected 8 science programs. They span a range of science cases from searches for NEOs to follow observational gravitational wave candidates, microlensing in our galaxy, our Lyris stars, supernovae, and young stars. Yes. What's next? Well, for next semester, we already put a full that we offer AEON on SOAR and the call for proposals for 2020A. We'll see. I hope. I don't know what. what will come out of it. I hope people will be enthusiastic and apply for time. So the number of nights will depend on the demand that we get. We also offered additional configurations, so we'll see what people are asking for. We will implement automatic data reduction with the pipeline and online. We want to see if we can extend to non-NOAA partners. What do I mean with this? We're for issues with our Brazilian friends, because they have 30% also of the SOAR time, to see if they're interested in adding at least some fraction of their time to AEON. And they actually run a queue a long time ago. It's just that they couldn't do it anymore because they didn't have the postdocs to run it. But in this way, it could be possible. So we'll see. And just improve things using knowledge from what we learned this semester. There's an AEON page at Las Cumbres. There's another one at SOAR. People want to learn more about it. Thank you.
Questions?
I get the impression you don't handle targets of opportunity at all. Is that correct? Because the queue is sort of predetermined.
No, we do. We do. And
how do you do that, then?
It's just that we only had like 5 nights so far. So it's small. So there are several gravitational wave programs that have target opportunity time at SOAR. So far, they had not triggered any target during an AEON night. But again, as I said, we only had 5 nights during the semester, so it's small number of statistics. I hope that there will be a trigger happening at one of the AEON nights. In that case, what people will do is they'll use the rapid response mode that Las Cumbres has. Las Cumbres has 3 modes: normal, time critical, which is mostly used for things like exoplanet transit or something that happens in a specific time window, and rapid response, which is something that needs to happen now. If a rapid response comes, and we tested it and it works, what will happen is that the target will get pushed up all the way to the top of the queue. Okay, and here, for example, here. If a rapid response came, that target will be pushed up to be first. And the current observation will be interrupted to the extent that if there's 3 spectra, for example, that were supposed to be taking half hour each, and the first one is already going, it will be allowed to finish, but then that's it. The second and the third one will not happen, and the observation, the rapid response, the target opportunity will get pushed up. And that's so it's all there. The mechanism are all there. It just needs to have a trigger come in.
You mentioned that observations currently require human intervention, and you said that there's no plan in the immediate future to have them done without human intervention. What's the reasoning behind that?
Well, as I mentioned, we will likely automate the target acquisition, and certainly the guide star acquisition. The guide star acquisition automation is just pending on the upgrade of the guiding system that we have right now. The target star acquisition, I envision that will be mostly automated for a significant fraction of the targets. Still, there will be targets that won't work, and you'll need a human being because the fields are complicated enough, where that there is ambiguity, and that's why we want to have a person there. There is a safety thing that our policy right now. We believe that having our operator there during the night, if anything happens, they can intervene quickly and correct things. If you wanted to remove the human element from that and still maintain a safe operation of the facility, the investment that you need to do is considerable. And you can ask GEMINI about that. They've done it, and well, They're not roboticizing it, but they remove the people from the mountain just during the night. I mean, you still have day crews every day, but it still needs investment of. Yeah, exactly. So.
Okay, let's thank Cesar again, please.
Yes.
Okay, next speaker is John Nation, who's going to talk about the Las Cumbres side of this project.
Hi, I'm John Nation. I'm a software engineer at Las Cumbres, and I'm going to be talking about the new LCO request APIs and also the AEON interfaces and things we've developed for SOAR for AEON. So I'm going to go over why we use APIs at Las Cumbres, the specific AEON interfaces, our old request API, and then the changes for the new request API. So API means application programming interface, and it's basically the communication protocol between two interfaces or the contract between your server and its clients. And the reason we use APIs almost everywhere at Las Cumbres is because it's really essential for us to have automated services interact without human intervention. So most of the APIs that we use at Las Cumbres are HTTP APIs. For example, here's a diagram for our scheduler of all of the different API calls it makes throughout one single scheduling cycle. And there's over 9 different API calls and over 4 different services that it makes calls to and gets replies back from in order to perform its operations. So these 5 things are the 5 separate interfaces that are necessary to integrate a telescope into the network. So these are the things that we've developed to get SOAR running within LCO. First, for telemetry, at a very minimum, we need to know from the telescope, from SOAR, whether they're available for scheduling or not. So just a Boolean, are you available right now? Are you not available? Beyond that, we want to know why you're not available. So those are the 2 things that SOAR gives us, is are you available and the reason if you're not available. And then that reason can be something like weather, different telescope issues, whatnot, and we can categorize that and display that back to the user. Then the next thing is proposals and time allocation. So we need a way to define proposals and to give them time allocated on each specific instrument on the telescope network. So SOAR has a way of defining all their proposals for each observing semester and assigning them time on whether it's the imager or the spectrograph for their telescope. And then our users have a way of viewing their proposal information through an API and viewing the time they have allocated and remaining throughout the semester. The next step is request submission. So this is what the observation portal does at LCO. It accepts requests from observers, and those requests are tied to a proposal and to an instrument class. So for SOAR, they have a SOAR proposal, they have a certain time on an imager or SOAR spectrograph, and they submit requests that way. The rest of the talk after this is going to be a lot about the request submission APIs and the observation APIs. So then the next set of APIs is for observation retrieval and status updates. Once LCO has a set of requests, our scheduler turns them into a set of scheduled concrete observations. So an observation is basically a scheduled request at a certain place and time. Then SOAR has to be able to retrieve all of those observations that are scheduled on it for any given night. And then throughout the night, as it takes data on those observations, it has to update the status of those observations. And updating the status is essential for the scheduler to know whether it needs to reschedule something that's failed or whether it's finished, and so that observation is complete. And then the final interface here is data submission. So this is only necessary if we need to get the final data product into the LCO archive. So for SOAR, in that case, they submit their data products to us at the end once they've gotten each data product, and we then ingest it into our archive. So for the request APIs, each observer has to define an observing request. And at a minimum, a request needs information related to the target, what you want to point at, the instrument properties that you want to take this request with, so exposure times, readout modes, filters, things like that. The windows during which you would like to get your data, and then your observing constraints, so things like air mass, seeing, lunar distance, stuff like that. Then scheduled requests become observations, and observations have to have all the same set of details as a request, except they don't need a generic window or a location because they've now been specifically scheduled on a certain place. So instead of that information, they have a specific where and a when. So they have a start and an end time specifically, and then a telescope, enclosure, a site for where they're scheduled. So here's our old API structure. At the very top level, we have a user request. And this is just a semantic grouping of requests. So if you have, say, a set of cadence observations on the same target, they would all be under a user request so that you could group them, see them together on the UI, query them together, things like that. Under that, you have one or more requests. And this is the smallest unit that is scheduled together on a certain telescope. Under a request, you have one set of constraints, one target, one potential location. So you can just have a single target, single constraints, and you can have one or more windows that it's observable in, and then one or more molecules. And this is basically the sets of configuration. So that can have exposures, filters, stuff like that. So here's an example JSON output API from a request with the old API. Some of the issues with this old API are some of the namings of things. So, what is a molecule? What is a user request? These names don't really make a lot of sense for what they are. Other issues is we have some stuff like we have spectra slit and filter, even though this is an imager, so it has no slit, but there's still a field there. And the naming for some of these gets a little jumbled between acquisition and guiding, so what supports which operations. So the purpose of redesigning this API was to support a wider range of observation types, like allowing us to do standards along with your observations scheduled at the same location. Support a wider range of telescopes and instrument sets, so integrating SOAR, but we also did some research on other instruments out there and their public APIs to see what types of things that we might need to set and have support for in our language. Increase the observation efficiency, so we would like to be able to cycle through multiple filters if you want to take RGB images or something in quick succession, and do that efficiently within our language. And then reducing duplication in our data model. So previously, we've had requests and observations stored in different databases, and requests and observations share most of the same data. So there's a lot of duplication of data in that model. in the new model, observations just have their specific where and when data, and then they point to their request. So they're completely sharing their data in that case. So here's the structure of the new request API. At the top, we have a request group, and this is just the grouping of requests. It's the same as the user request before. It's a semantic layer just to group a whole set of requests. In the future, it can be used for actual meaningful groupings if we ever were to implement andings of requests or things like that. Then you still have one or more requests. But now, several of the things that were under the requests are now under configurations. So a request has one or more configurations, which are what molecules used to be called here. And you still have a set of windows and a potential location for a request. But now the target and the constraints are under a configuration. So this allows you to have multiple configurations under a request that each have different targets and constraints and still get scheduled concurrently at one telescope at one time. Then we've also separated out and categorized some of the information that was in a constraint into instrument configurations, or in a configuration, into instrument configurations, acquisition configuration information, and guiding configuration information. And that's just to help organize it a bit better and make it clearer which properties affect which step. So I'm going to go through some specific features of the new language that were designed into it to help support SOAR and other future telescopes. So first, generic optical path elements. So before we had a specific field for filters, we had a specific field for slits, nothing else beyond that. So we made that more generic into this generic category for storing information about any type of grouping of thing that is in your optical path. So that means it can be filters, slits, gratings, diffusers, lamps, or any other things that we come up with in future instruments. All of this is defined in a configuration database we have in one place, and then it's used to validate against when submitting any request. And all of it's defined generically. So you define a category, you call it filters, you define each specific element of that, and then each specific element is validated against when someone submits a request with a field filter. The next thing is that we have multiple instrument configs under the multiple configurations in that step. So back here it's this, that we have one or more of these instrument configs. This is what allows us to take quick succession things of different filters or different exposure times or different readout modes. So any instrument property. So this allows you to loop through that set of things very efficiently without having to reacquire on a target or do any of that stuff that takes a lot of time. This feature is already available in SOAR requests, and it's going to be available on LCO in the near future. It's almost done in our telescope control software. The next feature of the API is that we have this JSON field called extra params in several of the structures. So we have it in configurations, instrument configurations, acquisition, guiding, targets. All of those have a field called extra params. The point of this field is to store any information that doesn't affect the scheduling, but is going to be used by the telescope control software or instrument control software to do something. So it's very useful for quickly trying out a new feature of an instrument or something and testing it out. It doesn't require any code changes or API changes. It's just a configuration change. So, this way, it's meant for fields that are only applied to a smaller subset of telescopes or instruments. So if a single instrument has a very strange parameter that it needs setting that doesn't belong in the generic API, it gets put in extra params. It's passed all the way down to the telescope control layer, and then that software can know what to do with that parameter. And the other feature, having multiple targets. Since targets was moved under configurations, you can have multiple targets per request now, one per configuration. This means that you can take an image of something and then go take a standard at a different target and all of that is scheduled together at the same instrument. So this wasn't possible before on LCO. This is already available in SOAR requests, and it should be supported in LCO in our telescope control software later this year, but it's already in the language. And then the last thing is separating out the guiding and acquisition. So this gives them their own sets of parameters, their own exposure time. This allows us to support more complicated and trying out new parameters for guiding and acquisition strategies. And also the guiding and acquisition strategies that are supported are also defined in one place in the configuration database and given their own overheads and then validated against through that. So here's the exact same request that was a few slides earlier, but with the new API. So it's a little bit shorter, a little bit less fields here, and also it's more categorized. So we have an acquisition config, guiding config, target. So all of this is just the new API here. So now I'm going to talk about some of the API operations that are available through the observing portal at LCO. And these are all things that you could hook into a TOM. Some of them are already hooked into the TOM, and some of them are things you could add to your TOM. So for request groups, that's the thing you submit. You can get or post request groups. So you can either submit a request group, or you can get a set of request groups with filters. You can get a specific request group using its request group ID. You can cancel a specific request group ID, and then you can validate a request group, get the max allowable IPP, and that's getting the amount of IPP that would be available to apply to this request group you want to submit, given its duration and how much you have available on your proposal. And this cadence endpoint, which will take a request group with a single request in it and a set of cadence parameters like period and jitter, and then expand that out into a whole bunch of separate requests that each have a window that fit your cadence. For request API operations, we have getting a set of requests with filter parameters, getting a single request with its request ID, and then a few related APIs of getting, for a single request, the air mass, which is the set of visible windows during its that is visible on a set of telescopes. The telescope states, so during its visible windows at these telescopes, what were the states of all of those telescopes? And this you can only get once they're in the past, because we don't know the states in the future. And then observations, and this gets your set of scheduled or completed or failed observations on this request. And for observation APIs, again, in common with most of our APIs, you can get a set of them for your proposals given filter parameters. You can get a specific one given an ID, and a specific observation includes the where, the site telescope it's scheduled at, the when, the state of it, was it failed, completed, canceled, and any error information if it was failed. So all of our APIs that I've described here and more APIs are available on our developers website, so developers.lco.global. There should be examples there and details on all the APIs. And all of our open source software is available on GitHub at github/lcogt. That includes our observation portal, which is the implementation of this request API. So you can see how things work through that project. Pretty much all our upper stack software is open source, even if it's in private repos right now. So our configuration database, our scheduler code. So if anyone has interest in seeing those as well, they can come talk to me and we can look through that stuff as well. So yeah. Oh, and other people are free to use our open source software for their projects. So right now, at least, I know Monet Telescope is using our observation portal and adapting it to their network. So yeah, if anyone has interest in that, come talk to us. So thank you. Any questions?
kind of the first question. So would it be correct then that any telescope that created the interface apparently?
Yes, for that set of 5 AEON things at the beginning, anyone that subscribes to those APIs could fit into our network in the same way SOAR does. Those are the 5 areas that it touches our network. Yeah.
Hi. So once we maybe create a project with our TOM itself, is that have the capability of being interfaced with an API?
So I'm not sure what you mean by create a project on your
Like
TOM.
we use TOM to, like, say, I don't know, access like our own local observatories, and it gets a target. Can we use our TOM to as an API to make a request to our own observations? Does that make sense?
Yeah, so the TOM has a plugin to submit observations to our observing portal through the LCO API. And so, yeah, in that case, you can submit observations to the LCO API through that.
Let's say I create my own facility, like say I want to create a facility that has a telescope and I want to submit an observation to that. Will that be able to, can I interface through the TOM as an API to send an observation through that telescope?
Yes. Yes. I think the answer is yes.
So yes, you can. It's designed to be extended, and you can add facilities interface. The facility itself has to have the API on the other side, of course, to receive and send that information, but the entire toolkit is intended to be extended, and we hope other facilities will join us.
So scheduling is done kind of above all of the telescopes with multiple facilities. What if a telescope had its own kind of scheduler? Would there be a way to bring that into a network, or do you need full kind of
no, so that would be fine,
control?
actually.
Yeah.
When we do scheduling, things are scheduled per class of instrument. So 1 meter sinistros scheduled together, or per telescope class. 1 meter stuff is scheduled together, 4 meter stuff is scheduled together. If you have a telescope that's its own class, either if it's its own aperture size or it has instruments that are unique to that telescope that aren't shared in a network, then it would be scheduled basically independently anyway. So in that case, you could just not schedule it in the LCO scheduler and instead use the interfaces to get your set of requests and schedule them yourself. Because that's just what our scheduler does. It gets the set of schedulable requests, does its thing, and then submits back the scheduled observations to our observation portal. So something else could fill that role.
Just to pick up on that, I think it's really worth emphasizing that there's 2 entirely separate channels that we're talking about here. One is where your TOM interfaces directly to another facility. That facility can do its own scheduling, totally independent of LCO, nothing to do with us, fine. Or if you participate in the AEON network scheduling, the way SOAR has, it goes through the LCO scheduler and then to the facility. And both are equally viable. And in fact, our next speaker is going to tell us about the second channel.
Is there an API I can use to tell me exactly why my observation didn't get scheduled?
So
Every astronomer would like to have one.
this is a joke question. Austin already knows the answer. You can't know exactly why your observation isn't scheduled due to the nature of the scheduler.
Yeah. Picking up on something Rachel just said, if I write some software that does all of these things, right?
Yeah.
That's one thing. But then actually getting permission to join the AEON network is a separate thing. That's a political issue or a whatever. So how do we do that? I mean, we have a telescope. that we might want to put into this thing. So I could do the software, that's easy. How do we actually get to be part of AEON?
That is something that I probably can't answer.
Okay, to pick up on that one, come talk to us. At this point, we are very happy to take new partners, and we'll happily talk through about the technical side of it as well.
In my intro talk, I showed this slide in which the publicly accessible telescope time was going down and the privately accessible going up. And for obvious reasons, the community, peer review community, is very eager to see access available to some of those private telescopes. Any more? Well, let's thank John again. Next speaker, Brian Miller, talking about AEON and GEMINI development still in the works.
Okay. Okay, thanks. This morning I'd like to tell you about some background on GEMINI for those especially who may not know the details of it, and get some information about what's available in this observing request and how to configure your TOM to use it. And this will give you an example of how to add a telescope plug-in to the TOM ecosystem. And it gives you some information about the schedule we're planning to build. As the name suggests, GEMINI runs twin 8-meter telescopes with coverage of both hemispheres from Cerro Pachon in Chile and Mauna Kea in Hawaii. And we usually call it GEMINI North and GEMINI South, but from the point of view of time domain, you might want to think about it as East and West, because the 6-hour time difference could be useful for some follow-up applications. So we support 4 facility instruments plus an adaptive optics system at each site. Up to 3 instruments plus the AO system are live and active at any one time. We have complementary instrumentation at the 2 sites. Optical imagers and spectrographs, near-infrared imagers and spectrographs in the AO systems. Altair in the north, which is a single laser and natural Geisler system, and the sort of unique at this time 5-laser multi-conjugate adaptive optics system in the south. We also have a viable instrument, a visiting instrument program. So you've got an instrument that can travel, and you'd like to put it behind 8 meters of glass. Come talk to us, and we can work out an opportunity. And if you have a proposal idea, we accept all sizes in a variety of timescales. Now, obviously, this is a proposal opportunity. That's coming out of the director's time bin up here, which is approved by our chief scientist usually, the director for short, urgent projects or special things like this. But if you need more time than is available here, or you get motivated from this to apply for more GEMINI time, here are the options. Poor weather proposals are can be submitted at any time. For bright objects, the worst conditions. If you have targets like that, this is a great way to get a lot of data, because we use it as filler. We have a lot, more bad weather than we know what to do with right now. Fast turnaround is an interesting and sort of unique proposal opportunity. There's deadlines once a month. There's no fixed tack. It's peer review. You send in proposals, you're going to get 5 or 6 back to review. It's good for short, intermediate things, trials, follow-up to get a little bit of extra time. It's been relatively popular. Oversight has been around 2. There's the usual semester process. So every 6 months going through the national time allocation committees at the partners. So most of the time still goes through that. And for very long, sort of more ambitious programs running up to 6 semesters, there's a large and long programs. Program which goes once a year, usually the March proposal deadline. So that's coming up soon. And it's good for monitoring programs over several years, as well as just when you need tens of hours of time. And there are a variety of observing modes. Of course, we're dominated by Q, which is excellent for the time domain. There are special conditions. You submit your observations. We're not robotic, but we observe it for you. And if you want to, you can look over our shoulder by eavesdropping, usually Skyping in, and you can see what we're doing or help us out with an acquisition, something like that. If you want to come, you're welcome to. Is the classical visitor mode, useful for if you're doing something sort of non-standard, or you need some real-time decisions, or you just want to come and visit. It's possible, but people don't take us up on that very much. A sort of a combination mode, which is really good, is priority visitor observing, which is a lot of our large programs do this. You come for an extended block, like a couple weeks, and you can pick and choose the time when you observe your program in that period, and we do queue back up when you're not observing. And as been mentioned, we now do almost all of our observing from the base facilities in Hilo and La Serena, instead of from the summit. So it's almost remote observing, but not really remote observing, and we don't really offer a remote observing option in general. So one important bit of information for this opportunity is what we call what we mean by target of opportunity. For us, a TOO target is anything whose coordinates is not known at the time of the proposal. And then there are two types of TO observations that you can request. One is the rapid, which requires response or observing within 24 hours, so the current or upcoming night. It can't have any conditions, constraints, and if it has the proper authority, it can interrupt ongoing observations. You need to specify in your proposal if you want to have this capability. And the thing you should know is if you interrupt someone's observation and they lose time because of it, the time comes out of your program. More typically, we don't get a lot of these, but this was put in for LIGO follow-up, for GRB follow-up. It's useful for that. Standard TOOs are anything that just comes in, during the semester and it's just fitted into the next Q plan along with everything else. So it doesn't require any urgency for the next day. You can set timing windows. So a lot of supernovae follow-up uses this. You say, I need the observation within 2 or 3 days, and you can extend those timing windows as needed. And usually if you're doing follow-up of rapid TOOs, you should have some conditions better than any, we call them. You can get more information on that down here at this website. Another important thing related to TOOs is our policy on competitive TOOs, which we updated after the sort of excitement and chaos of the LIGO follow-up in 2017. So this webpage defines the policy, but the short summary is here. We give priority to existing Q programs for follow-up over any DD proposals that come in at the last minute. If multiple requests come in for a target, if there's time, we work with the PIs to work out some reasonable plan. If not, the prioritization is given here. It's basically first come, first serve, assuming all else is equal, like the same TAC rank. And then we try to keep track of what the order in which things come in and do them in that order, as long as it's reasonable for given other considerations. And if you get multiple requests for the same configuration, like the same instrument and the same grading, we may share the data with everyone who requests it. The main thing is we get on the sky, we start taking data, and we sort of sort out the mess later, while trying to maintain fairness and not repeat things. So for this observing opportunity, there are 50 hours of director's time available at both sites. One thing you should know is that we will be trying to balance the time between the sites and over the full period. It doesn't have to be exact, but that's what we're going to try to do so that we don't impact the rest of the queue too much. So to help us out with this, we ask that in your observing time request, separate the time you need by site and instrument as given here, like GMOS versus flamingos, north versus south, and specify in your text whether it's okay to observe at the other site with sort of comparable instrument. Like if you want flamingos too, but GNERs would work, please let us know. It gives us more flexibility and gives you a higher chance of getting some time on the telescope. So the instruments that are available, we have a wide set, but not a complete set of the instrumentation. In the southeast, We have GMOS, which is our workhorse and most popular instrument in the optical imaging over a 5-arc-minute field, long-slit IFU, MOS. One thing to note, rapid TOs with MOS are not possible because you need at least a week to cut the mask and get it in the instrument. Flamingos 2 is our workhorse, near-infrared imager and spectrograph. Both of these are on the telescope most of the time unless they're off for maintenance. And down here are some links. It would be interesting because you can go to these web pages to determine what our TOO status on a given night is and what instruments are on the telescopes. Fortunately, there's no API for that yet, but you can scrape those web pages. So in the northwest, we have GMOS North, which is basically the same as GMOS South. And then we have a set of near-infrared instruments, the NIRI imager, NIFS, IFU spectroscopy, GENERS, long slit spectroscopy, which is sort of intermediate spectral resolution with a cross-dispersed option. All these three are also available in natural guide star and laser guide star AO modes with Altair. LGS standard target opportunities are possible if you give us like 3 days of notice, because we need to send the targets to the U.S. Space Command and get permission to propagate the laser at those positions. Rapid TOs are not possible yet because of that. A couple of visitor instruments are also available, but those will have scheduling restrictions because they're kind of done more in blocks than the rest of them. GRACES is a optical high-resolution spectrograph, which actually uses the Espadon spectrograph over at CFHT. And we run a 200-meter fiber from the GEMINI focus to CFHT. And Elapeke is a optical spectral imaging camera, which is sort of always mounted, but is still sort of used in blocks by the team, and we're slowly training our own staff to use it. It provides very rapid readout mode as well as a speckle option. So that's what's available on GEMINI. As part of your proposal, you do need to include all your overheads. So there's some suggestions on how to do that. The basic ones like readout time and offsets, you can dig through our instrument web pages or bring up the observing tool because it's all built into that. The integration time calculators also have the same information used by the observing tool, and the output page of the ITC will give you an estimate of the time needed with overheads for that observation that you put in. So you can basically copy that in. But you need to add an additional overhead for our baseline calibrations. It's usually about a 10% factor, and those factors are given on this web page. It depends on the instrument and mode. All right, so assuming you get time on GEMINI, then you will need to prepare a phase 2 or the detailed observation definition with our observing tool. So I'll go through, assuming a lot of this is going to be target of opportunity observing, I'll go through that process. The beginning, you start out by working with a context scientist to define some template observations, which are set to a status called on hold, which you'll see has this little gray icon up here. It's basically the completely defined observation, ready to go, but with no target. And because it's on hold, our scheduling system won't pick it up yet. So the trigger sequence is something like this. You copy paste the template to create a new observation, fill in the target information, add some tweaks like the position angle, guide star, set the status to prepared, which turns this green. You sync it, which uploads it to our databases, and that does the trigger. Announcements happen depending on the type and so on. And you can upload a finding chart or make it available to us. And then it can then be scheduled, or the observer is notified that this is available. And this is done manually with the OT, or of course, more appropriate for us, is that it can be done programmatically via a URL API. There are a variety of parameters. Basically what happens is you submit the target information and other parameters via this URL, and the observing database takes care of that whole process of doing the copy, putting in the information, changing the status, and making the trigger. That documentation is here at this GitHub site, where I provide some example scripts including some routines for doing guide star selection. Fortunately, you shouldn't need to know too much about this particular API because the Tom Toolkit is now your interface. We use this API as part of the GEMINI Tom Toolkit plugin. Here's the standard user interface for the plugin that you'll get with the Tom base, the standard installation. You get access to all the different fields possible with the API, along with some validation checking. The one thing that it doesn't do is guide star lookup because we wanted to reduce dependencies, but I'll talk a little bit more about options for that in a bit. In order to configure your Tom for your particular program, you need to follow this. You need to customize the facilities section at settings.py. So there's a part up here where you need to put in the URLs of the servers. This ODB test servers are available today if you want to try this out. These are just test databases. When you go into production, you just need to change this, remove the test, so it's GSODB. You need to validate the connection with called a user key password. Those are associated with the email address that's in your program. You can get those with the observing tool. We can try out that this afternoon if you want to do that as well. And then you need to put in a section related for each of your programs. You need to put in a list of these templates that you defined. So for example, here, 1, 2, and 11, 1, 2, and 11, those have to match, and you can put in a little text description there to remind yourself what those are. All right, so guiding. While not required, if you don't give us a guide star, the OT will try to find one for you. It is recommended, I think, that you try to see if one is available. That is because guiding is really required for our active optics system to make sure you get the image quality that you would expect. And a lot of the guiders, like GMOS, have relatively small fields and they're not symmetric. So there's no guarantee you're actually going to have a guide star you can use for a given position angle. So that's why we have this GS Select Python package available, which does a similar guide star selection to what the OT will do. It also has sort of a find position angle feature, which we have never implemented in the OT yet, which if you don't care what the position angle, say, of your slit is, it'll just find the best available guide star and set the PA so that it's inside the guider field of view. And it is available for the Tom Toolkit, but not in the base. You have to add it on as a sort of extended plugin. So from this repo in GitHub or from pip, you can install this and then override the plugin which in Tom base by updating the facility classes section of your settings file here, just like this. And then you get the guide star selection. And there are a bunch of extra fields now in the UI, the parallactic angle modes, other instrument selection options, and conditions, constraints options that used by the guide star selection. So for PA modes, there's, of course, fixed, allowing 180-degree flip, which is useful for a long slit. Just find the best PA option that I mentioned, and setting the parallactic angle for a given time. So now I'm going to show a little video similar to what Jamie showed the other day, but it shows how all these pieces fit together and what it looks like in the GEMINI environment. Let's see if this works. Yeah. Okay, so I've imported a target from ZTF. I'm checking the observability, and they're available at the 2 sites. And here's north and south. So I'm going to submit the observation. This is the version of Tom Toolkit from last January, so it looks slightly different, but you get the idea. There's a grouping label. I'm going to do parallactic angle mode, so I set date and time when this might be observed, target brightness. I'm going to set air mass constraint, add a little note for the observer, or a URL for the and now it's going off and actually doing the guide star selection and did the trigger. Here's the record of the observation in the Tom. If I go over to the observing tool now in sync, there's the new observation with all the information filled in. My constraints, the guide star, and the slit along the parallactic angle. Of course, the real power of this is being able to do things automatically and set up queries to alert servers. So I've defined one, and I've set it up so that everything that matches my query parameter is triggered. So here are two things that it found. It already submitted the observations in the south. They got a rapid trigger, so the observer will see this pop up when it comes in. There's the basic information about that. And then GEMINI, for the northern target, I have to change my authentication so I can see northern programs. And there's a standard trigger for GEMINI North. So this afternoon, you can do exactly the same thing as this with our test system and not bother anyone on the telescopes. And there's in the TOM the record of those observations. All right. So there are a bunch of things that be improved. The interface is very basic. You can do customizations if you don't need all the fields, such as Jamie showed. A few things that could be done in your development projects are, say, running this guide star selection and seeing the results before you do the final submission so you can make any tweaks as needed. I'll mention some other things in my talk tomorrow as well. Another thing that's important to know is that the API is rather basic and it does not support non-sidereal targets very well. We use ephemerides to handle all non-sidereal targets. Those are not handled by this API. As it is now, you would just need to sort of give us the horizons name, say, of the target, indicate it's a non-sidereal target, and let the staff person query horizons and download the ephemeris using the OT. It's kind of clunky, but it's the way it is at the moment. If there are going to be teams applying for time to do non-sidereal follow-up with GEMINI, we can talk about trying to update the API. We have a couple ideas of what we could do in the short term to make it at least a little bit easier, like having the ODB do the horizons query for you. So please come talk to me if you need this capability. Again, you have to do something relatively simple, something we can do by our December release. So that's GEMINI now. I'd like to spend, the rest of my time talking about GEMINI in the future. So as is mentioned, a lot of what we're doing is based on the Elma Green report from 2015 about how to optimize the US system. And the GEMINI board has also factored this into their strategic vision, saying we want GEMINI to be really important using its queue system plus the location to be important in the LSC follow-up game. So one of the recommendations was for a high throughput broad wavelength spectrograph, and we're implementing that or instantiating that as part of the Scorpio instrument, which just went through its critical design review. It can cover from G to K simultaneously over a 3x3 arc magnetic field using 7 dichroics, or you get a single object long slit spectrum over that whole range at R about 4,000. And it should be operational by 2023 when the LSST main survey starts. The other recommendation was for all NSF facilities in Chile to collaborate for follow-up studies, and that was the impetus for a lot of the impetus for AEON. And we are going to enhance our support for this by a couple of very large software projects we're just kicking off. One of them is the OCS Upgrades Program, and the other one is GEMMA that I'll talk about. This is a very large effort to basically rewrite all our high-level software because the current system is 20 years old, it's hard to maintain, it has limited capabilities. It's time to just start from scratch. So we want to rethink the whole purpose, the UI, some first principles, make it easier to use, especially the phase 2s, include new features that we can't put in now, which are really important for implementing sort of scheduler, make it much more API driven, and make it easier for us to maintain. One idea that came out of this was to have sort of a phase 0 tool to find the instruments and modes that are suitable for your program. So you can just put in, say, I need a near-infrared spectrum at R of 2000. And it will tell you, well, we've got F2 engineers that can do that. I need to do an optical spectrum of something with good wavelength resolution. There you get ghosts and graces. Or high-resolution imaging is going to give you the near-infrared imagers with laser guide stars. If you have coordinates, then of course it can further limit the options or even pick something for you, which might be useful for rapid follow-up. So part of the principles that we were working on is that we want to have GEMINI North and South observations in the same program, so no more of this switching keys like you saw in the movie, which will drive us to a single database somewhere in the cloud and web interfaces that are task-specific for different things that you're doing. We want to move away from the rather abstract condition percentile bins we have now and go to physical conditions on target, build them around the ITCs, give you overheads, calculation, execution probabilities, and much better management of calibrations so you get the proper things that you need. So we are just refining the requirements and concepts right now. We're going to have an internal review in about a month, and then go into more detailed design phase and start building this thing out. We've been also doing a lot of prototyping, modeling, deployment process, and so on. This is an example of what it might look like. We've been rewriting our execution tool, the thing that actually takes the data and goes through the sequences using the sort of software libraries and technology we're likely to use for this. And finally, there's GEMMA. We're going to implement an automatic scheduler and the necessary APIs, which will probably give a similar capability to what John just showed for Las Cumbres, hopefully with a similar format as well, using $26 million supplemental funding that we received from the NSF last year. So it's going to fund these 4 big things: an MMA outreach program, a new multi-conjugate AEO system for GEMINI North, and its control computers, the real-time scheduler, and the APIs, and real-time capability. I'll talk more about that tomorrow. And so GEMINI working now within AEON, within our sort of limited capabilities and APIs, but we're trying to reimagine and rebuild the whole thing to give more expanded, more capable APIs, dynamic scheduling with the 2 telescopes together, a sort of a mini network, and maybe other 8-meter class telescopes could join later. Data reduction pipelines and archive improvements I'll talk more about tomorrow to try to close the loop. And we hope that all of this will enhance the science from GEMINI, from AEON, LSST, and it should also benefit all users, not just time domain with the future improvements. So thank you very much.
Thanks for that, Brian. Just a question about the policy change you mentioned at the end there of going away from the sort of magically defined conditions to something a bit more practical. While I generally like that idea, what is wrong with the idea of doing something like a signal-to-noise constraint, which seems to be more practical still?
Yes, good question. We would like to do that. That was always in our very, very long-term plan for years. As part of all the discussions, internal discussions about the OCS upgrades, we thought a lot about signal-to-noise as a constraint. It's not going to be in like version 1 of the OCS upgrades, but we're hoping to move in that way with the improvements to all the data reduction pipelines, building in the ITC more closely so you can actually use that if you don't have the result from the pipeline. We think it's possible, but it's complicated. It will be probably more years down the road, but we are moving in that direction. We at least want to make it possible that we could do that. We don't want to inhibit being able to do that. And we're taking a lot of the lessons learned from CFHT and other people who have done that.
I had a couple of questions. The first one was, how many science programs have used TOM or AEON to trigger Gemini? And have you seen any bloopers so far?
I think Curtis is the only one that may have tried to use it so far. They've configured his new SNCs.
So nothing has actually triggered.
Not yet, but it works. We can try it this afternoon.
Okay.
You can actually go through all the steps.
And the second question I had was, the Finder chart usually on the Gemini Phase 2 tool, you're uploading files.
Yeah.
I didn't see anything on the TOM to upload.
That's another weakness of the current APIs. You can't upload a file with the API. You would have to do that with the OT or in that little note box. If you put a URL in there and have the Finder chart somewhere at that URL, then the observer can just copy paste that into the browser. Yeah, that's probably the easiest way to do it.
And is there if first time it's used live, if there's a blooper, can it be canceled?
Canceling is another limitation.
Okay.
If you need to cancel an observation, you would need to do that with the OT. You can set it back from this prepared state to the on hold or inactive. And then probably so that it's clear to the observer or people what's going on, you probably should send an email to an email exploder to say, oh, I withdrew it. People have done that. So again, the current system is a little clunky. In the future, it should be much more streamlined. It'll act much more like the less cumbrous system where you can just withdraw it programmatically. Oh, one thing about the API, while it hasn't been used in anger with a TOM yet, the API has been used in the past, like for GRB follow-up.
Okay, I'd like to jump in with a comment. We have a comment from the Blue Jeans channel. Shri says, there are two different needs, TOO and samples. Examples for the latter include going after a sample of interesting binaries or host galaxies. There is a lot of focus on TOO, which is fine, but TOO will not dominate the entire allocation budget.
Sure.
For all astronomy, observing efficiency matters. Gemini seems to have an incredible overhead. The overhead should be no more than a few minutes. Is that something you could speak to?
True, I focused on TOOs because of the kind of the focus on that in this meeting. Yes, it's you're welcome to apply for other types of time domain science. It's not just TOOs. It doesn't have to go through this. I thought this was important for this crowd. Our overheads, overall, I think are not too bad. It depends on the instrument and the mode. For imaging, we're on Sky in it depends on the slew. Often we're limited by the slew of the dome, the movement of the dome more than anything else. For long-slit spectroscopy, it's within 10 minutes. It depends on the brightness of the guide star, the density of the field, that sort of thing. But it can be relatively quick. So we try to keep those as low as possible within the engineering constraints of the telescope. And we're always trying to get those lower if we can. The automated system, like the automated scheduler and other things that we'll do related to that, we'll hopefully try to get that a little lower. Yeah.
I will preface my question with the phrase "asking for a friend." Okay.
Yeah.
And I have a question here from a colleague. It says, in terms of automated triggering of a target of opportunity, is there a way to get the current weather conditions programmatically to maximize the trigger?
No. It's another weakness of the current system and what the motivation for this whole OCS upgrades thing. The information is available on various web pages, but it's not accessible easily programmatically right now.
Okay, well, that's timely. Session time end is here. We have a coffee break. Let's thank Brian again.